Welcome to this explainer. Today, we're taking a seriously fascinating journey through one of the most exciting landscapes in modern condensed matter physics. We're going to explore exactly how the field has systematically moved beyond its early, rigid constraints to reveal a much richer and honestly, a highly adaptable framework for understanding macroscopic quantum coherence. So if you think you already know superconductivity, well, prepare to have your assumptions challenged. Okay, let's dive right into the deep end. What we're dealing with here is a high-level diagnostic map of advanced superconductivity architecture. And yeah, it sounds and looks incredibly complicated, right? That's because modern physics has had to evolve way beyond simple models to describe what's actually happening inside these incredible materials. But don't worry, we're going to use this explainer to tease apart this advanced architecture piece by piece, and then bring it all back to the basics so you can fully grasp the big picture. Over the next few minutes, we'll dismantle the classic rules through 6 stages: the 1957 superconductivity blueprint, breaking time and space, pushing the interaction limits, multiplying the complexity, unconventional shapes and spins, and finally, the new quantum map. Part 1. The 1957 superconductivity blueprint, establishing the original rulebook of macroscopic quantum coherence. To really understand where we're going, we first have to understand exactly where we started. The 1957 BCS theory was this incredibly elegant, Nobel Prize-winning foundation, but as we're about to see, it was also remarkably rigid. For decades, this standard theory relied on 6 very strict constraints. It basically provided the universal blueprint for weak coupling macroscopic quantum coherence. It assumed everything in the system was perfectly neat and tidy. We're talking instantaneous attraction, perfectly uniform spatial parameters, and a very weak interaction strength. I really want you to keep this specific checklist of constraints in your mind: instantaneous, homogeneous, weak coupling, single band, isotropic, and non-magnetic. Got 'em? Good. Keep those logged in your memory because the rest of this explainer is essentially a thrilling intellectual heist. We're going to systematically break every single one of these rules to see what modern physics has uncovered on the other side. Part 2. Breaking time and space, moving beyond static potentials and uniform states. Let's get right to our first targets and kick off this heist by breaking the instantaneous and homogeneous constraints. Now, there's a massive shift from static to dynamic going on here. The original BCS theory just assumed electrons interacted instantaneously, but in the real world, the heavy ions of a crystal lattice move way slower than those zip-fast electrons. The Migdal-Eliashberg theory updates this by actually accounting for the retarded dynamic response of those heavy ions. It effectively replaces that old static BCS gap with a highly dynamic, frequency-dependent one. Eliashberg theory completely rewrites the classic parameters. It tosses out instantaneous timing for a retarded dynamic interaction. It swaps a constant mass for a renormalized effective mass. And by doing that, it vastly expands our accuracy range, allowing us to finally describe strong coupling materials like high-pressure hydrides that the standard BCS model simply couldn't handle at all. Next up, we've got to break the homogeneity rule. Look, real-world materials are messy. They've got impurities, magnetic fields, and totally complex interfaces. You can't just assume a perfectly uniform state. Enter the Bogolyubov-de Jeans framework. By modeling discrete energy levels for quasi-particles trapped inside vortices, which are essentially these swirling little tornadoes of supercurrent, it lets us simulate complex materials from the atomic scale all the way up, proving definitively that the quantum world is anything but uniform. Part 3. Pushing the interaction limits, evolving past the boundaries of weak interaction. Having entirely shattered our assumptions about time and space, let's scale things up and shatter the idea that quantum interactions must always be inherently weak. By deliberately pushing the interaction strength limits, we move right through what's called the BCS-BEC crossover. On one end of the spectrum, we have the classic BCS limit, weakly interacting, highly overlapping Cooper pairs. But as we crank up that interaction strength, we slide smoothly through a unitary regime, all the way to the BEC limit at the other extreme, where we find tightly bound composite bosons. And honestly, the most incredible part? This smooth transformation involves absolutely no formal phase transition. It is one continuous spectrum of physics. Part 4. Multiplying the complexity, exploring the effects of multiple electronic bands. All right, we've broken 3 rules. Let's keep this momentum going and scale up the complexity even more by breaking the single band rule. What actually happens when multiple electronic highways get involved? Using magnesium diboride, or MgB2, as a brilliant case study, we can really see the wild effects of multi-component superconductivity. In this specific material, you don't just have one band crossing the Fermi level. You actually have distinct pi and sigma bands, and each has its own superconducting gap that interacts with the other. This multi-band reality introduces incredibly exotic consequences, like collective excitations we call Leggett modes, and even mind-bending half-quantum flux vortices. Before we picture the ultimate result of this multi-band chaos, we need to quickly learn a wild new vocabulary term born directly from these systems: type 1.5 superconductivity. Now, traditionally, physics divided materials into type I or type 2. But in multi-band systems, multiple coherence lengths create competing forces. You get short-range repulsion clashing directly with long-range attraction. The result of that clash? Macroscopic vortex islands, completely separated by vortex-free regions. Because of a really specific, attractive sweet spot in those competing forces, the vortices clump together into dense little islands, leaving these peaceful, vortex-free Meissner oceans right in between them. It's a beautifully complex state of matter that literally cannot exist under the old single-band rules.
Part 5. Unconventional shapes and spins, shattering the final symmetry and magnetic rules. We're down to the absolute final constraints to cross off our intellectual heist checklist: isotropic and non-magnetic.
Okay, let's really dive into this intriguing question because it completely flips the standard model on its head. Standard BCS theory said that phones, the physical vibrations of the crystal lattice, were the one and only glue that could hold superconducting pairs together. But what if the glue is actually magnetism? By breaking the rule that pairing has to be perfectly spherical or isotropic, modern physics fully embraces these exotic harmonic shapes. When the glue is driven by electronic excitations, like spin fluctuations near magnetic instabilities, we get shapes like the four-leaf clover D wave, which is famously seen in high-temperature cuprates, or even the P wave. These nodes, the literal gaps in those shapes, are direct, undeniable signatures of this unconventional magnetic glue.
Furthermore, when we look at materials lacking a central point of symmetry, meaning they break field inversion symmetry, we witness a crazy phenomenon called parity mixing. It's fascinating because the gap function actually becomes a hybrid. An even parity singlet mixes directly with an odd parity triplet. This isn't just a mathematical quirk even. It induces exotic magnetoelectric effects, like helical phases where the order perimeter spatially varies. I mean, we are way beyond the 1957 rulebook now.
Finally, let's completely smash the non-magnetic rule. Traditionally, magnetism was seen as the absolute enemy of superconductivity. The thought was it would violently break apart the paired electrons. But in spin-glass superconductors, this relationship is highly dynamic. In a reentrant phase diagram, as the temperature drops, the material becomes superconducting. But as it drops even further into the spin-glass region, the superconducting gap actually increases with temperature for a brief, totally counterintuitive period, before vanishing. It reflects an incredibly delicate balance of competing quantum orders. Part 6. The new quantum map. Synthesizing a grand, infinitely adaptable framework. Wow, what a journey. We have systematically broken every single one of those 6 foundational constraints. So let's step back for a second and synthesize our new reality. What does this upgraded universe of physics actually look like? If we plot our journey on a universal map, it reveals our origin point down at the foundation, standard BCS theory. But as you move along the axes, increasing system complexity vertically and increasing interaction strength horizontally, you can literally track all the theories we just explored. Bogoliubov-Degenitz, Ilya-Aschberg, the BCS-BEC crossover, going all the way up to parity mixing and type 1.5. Breaking the constraints didn't ruin the picture at all. It expanded it into this incredibly rich, vast landscape of quantum coherence. The 1957 BCS theory was never meant to be a static destination. It was just the initial architecture. By systematically relaxing those early constraints, physics has built an infinitely adaptable framework. And this isn't just about laboratory curiosities anymore. This advanced architecture is capable of describing everything from the hunt for room-temperature superconducting hydrides, right here on Earth, all the way out to the ultra-dense cosmic cores of distant neutron stars.